Okay, so we were talking about the turning performance and the VN diagram, which is related to that. So if you remember, before that we started with a steady level flight condition, and in the steady level flight condition we have two force equalities. Lift should be equal to the weight, and the thrust force should be equal to the drag. And then we talked about climbing flight, and in a steady climb, lift force actually has to be less than the weight, because a part of the weight of the aircraft is supported by the thrust force. And when we come to the turning flight, we were talking about the level turn, the sustained level turn maneuver. And in that case, lift force has to be greater than the weight. And to see that, we can refer to this diagram. So this is for a sustained level turn maneuver, and we say that the altitude of the aircraft remains constant, so there should be no net force in the vertical direction. So the lift force still has to balance the weight, but the vertical component is used for that, and the horizontal component is used for turning. So to change the orientation of your flight path, you need to create a lateral acceleration. And for that lateral acceleration, you use the horizontal component of the lift force. So to study this motion, we use two equations. First one is the force balance equation in the vertical direction, and in the horizontal direction, we have on this force, and that force should be equal to the centrifugal acceleration for the turning. So if you combine these two equations, you end up with this equation, and at this point we define a new variable, a new parameter called the load factor, and this load factor shows how high the lift factor should be compared to the weight. So for turning flight, this load factor has to be a number greater than 1. And then we obtained these two equations. So this is for the radius of turn, and then there's a similar equation for the rate of turn. This is the angular rate. And if you look at these two equations, for a faster maneuver, you need a high load factor. So if you want to make a very fast turn, this end has to be a large number. It should be as large as possible. And if it is 5, for example, then that means the lift force should be 5 times the weight of the aircraft, if you remember the definition. And in the case of a level turn maneuver, that will mean that during that maneuver, the total acceleration for the aircraft will be 5 times the gravitational acceleration. So the question then becomes, well, for a highly maneuverable aircraft, you need a high load factor. And the question is, how high of a load factor can an aircraft have? So if you can find that number, then that will tell you how maneuverable your aircraft is. Okay, so if you want to study the performance of an aircraft, then you will need to find the load factor number. And when you find the load factor for which the aircraft can safely perform a turning maneuver, then that will tell you how maneuverable your aircraft is. Okay, and if we come to last Friday's lecture, which is this one, so on Friday we studied how high of a load factor an aircraft can have, and it turns out that this depends on the flight speed. For that we use this diagram. This is called the VN diagram. We have velocity at the horizontal axis and load factor in the vertical axis. And if you look at this diagram, if your flight speed is very low, then you can't really have a high load factor, and this is very reasonable, right? Because at low speed, your aircraft cannot even fly, let alone perform a maneuver. So for this aircraft, for example, at this speed, some little bit over 50 meters per second, so this corresponds to the stall speed, and at that speed, it can barely fly. So the load factor it can have at most is 1. So that means it cannot perform a turning maneuver at the stall speed. Okay, so you need to have a higher speed. And so the load factor is lift divided by weight. So this is the maximum load factor. So that means we are looking at the maximum lift force an aircraft can ever have divided by its weight. And the lift force, for the maximum lift force, we write 1/2 rho v squared S times CL max. And as you can see, it changes with as a function of speed, and it has this parabolic relation with speed, right? So from here we conclude that if the flight speed is increased, then the maximum load factor your aircraft can have increases. And since this relation is quadratic due to this second power, at very high speeds you can theoretically have very high load factors, but that's not the only limiting factor. If you just consider the aerodynamics, you can say that this aircraft can go up 9 Gs, for example. But again, it's not the only limiting factor. You have to consider other things as well before you can say that your aircraft can safely perform a maneuver at that speed. Well, the most important limitation is the structure. The structural strength of the aircraft is very important, because if you want to perform this maneuver with a load factor of 9, that will mean that your wings will have to carry a weight that is 9 times the weight, and that's a huge load. And unless the wings are strong enough, you will have problems. So in this Venn diagram, you have to show the structural limits. So let me go back to the last slide. Okay, so this is the same, the aerodynamic limits, load factor, and then on top of this you need to put the structural limits. So if the wings are strong enough to carry 100,000 newtons, for example, and if you know the weight, well, you should know the weight, obviously. So you divide that maximum number to the weight, and whatever the number you get will be the structural limit. So on top of this parabolic curve, you put this limit, and this is the structural limit, and you should never exceed this limit, otherwise your aircraft will be damaged. Okay, and for sustained level turn maneuvers, there's a third limitation, and that third limitation comes from the engine, from the propulsion system. During the maneuver, you want the speed of the aircraft to be constant as well. Okay, so you need to satisfy this equality. Thrust is equal to the drag force. And when you have a very large lift force, then the drag force will be very large as well. And at that point, the engines can become the limiting factor. So there are 3 things that limit the load factor. So for this example, the C-130 aircraft, so this is what we had. So this is the aerodynamic limit for the C-130 aircraft, and the propulsion limit is this one. And as you see here, they intersect at this point, and at speeds lower than that limit, the critical one is the aerodynamic one, because this is the lower limit. And at speeds higher than that, the critical limit becomes the propulsion limit. So if I ask you to find the maximum load factor an aircraft can have, you need to check all 3 limits and then give the answer based on that. If you just check the propulsion limit, and if it seems to be okay, you can say that this is a safe number, because if the wings are not strong enough, the aircraft will not be able to safely perform that maneuver. Okay, so let's come to today's topic. Today I want to talk about the other two maneuvers related to turning flight, which are the pull-up and pull-down maneuvers. There's one important difference between these pull-up, pull-down maneuvers and the steady, sustained level turn maneuver. The sustained level turn maneuver is performed in the horizontal plane, but these maneuvers are performed in the vertical plane. Okay, so I don't know if you can see that, but here there's an F-16 aircraft, and this aircraft is making this turning maneuver in the vertical plane. And there are just two force equations we use for that maneuver. There are no forces in the horizontal plane. So if you look at the top view of this maneuver, then there will be no horizontal forces. So we only use these, well, there are no lateral forces. It's a better way of saying that. Okay, so just like what we always do, we write two force equations. One for the forces in this direction, and the second equation is for the forces that are perpendicular to that. So this gives us two equations. The first equation is this one. So you have thrust force, and the drag force is in the opposite direction, so it has a negative sign. And the weight of the aircraft has a component in that direction, which is weight times the sine of this angle, sine theta. And in general, it should be equal to mass times the acceleration. So if the aircraft, the speed of the aircraft changes, then the right hand side should be equal to that. But if you want speed to be constant, then you can say the right hand side is going to be 0. And the second equation is in this axis, and that equation is shown here. You have lift force, this is the positive direction, and the component of the weight force along that direction is weight times the cosine of this angle, cosine theta. And there should be an acceleration in this direction for the turning to take place. Right, the centrifugal acceleration will be in this direction, and you write it as m times v squared over r. Okay, so you have these two equations. So what makes this pull-up maneuver different than the level turn maneuver is these theta terms. So because of these theta terms, the pull-up maneuver is different, because at every instant during the maneuver you have a different force relation. That's because these, for both of the equations, depend on theta. If you go back to the level turn maneuver, so in this equation you have this angle, the forces, the equation depend on the bank angle, but the bank angle doesn't change. It's a constant number during a maneuver, right? You start the maneuver and you can keep this number fixed. But in the case of a pull-up maneuver, it's not the case. You start the maneuver here, and then as the aircraft turns, the force relation changes. Okay, so if you, for example, consider the beginning of this maneuver, if you assume that the aircraft performs the maneuver from a steady level flight condition, then at the very beginning the theta is equal to 0, and if you insert theta is equal to 0, this first equation becomes thrust is equal to drag, assuming that the acceleration is 0, and the second equation becomes this, right? The cosine theta term becomes 1, and from there you get lift minus weight is equal to mv squared over r. And for that you can obtain an expression for the radius of turn, and this is very similar to what we did earlier. We use again the load factor definition, and the derivation is given here. If you look at what is done here, you basically you're trying to find an expression for r, so you just put this r, leave this r alone on one side, and on the other side you have this. And to be able to use the load factor, you divide the denominator by, or you take this into w parentheses, and that gives you n minus 1. and then you introduce a gravity term to both sides of the fraction, and in that, this is what you get. The radius of turn is given by v squared divided by g times n minus 1. And again, let me just remind you that this is valid only at the very beginning of the maneuver, only when theta is equal to 0. So if you want to write an expression for this situation, for example, where theta is a non-zero number, then your equation should involve theta term. But we don't really worry about that in this course. So this note is important. It just says what I already told you. These equations are valid only instantaneously at theta is equal to 0. And unlike a level term maneuver, it is very hard to sustain a pull-up maneuver due to the fact that these force equations depend on theta. So you can perform a level term maneuver by fixed controls. The pilot sets all the elevator, aileron, rudder, all the controls to the correct values, and then the aircraft can perform a sustained level term maneuver without changing anything with the fixed controls. But it is not the case for the pull-up maneuver. For the pull-up maneuver, if a pilot wants to perform a perfectly circular loop like that, so the aircraft wants to perform a perfectly circular path in the vertical plane, then the pilot has to constantly change the controls, the elevator and the throttle, according to these relations. So for example, the lift should be changed as follows. It should be changed as W times cosine theta plus mv square over r. So as the theta changes, the pilot has to change. So this is not v, I'm sorry, this should be lift. So the lift has to be changed continuously throughout the maneuver. And as I just wrote here, it is really difficult to perform a sustained pull-up maneuver. Okay. And then the next maneuver is the pull-down maneuver. This is how a pull-down maneuver is defined. So notice that this aircraft is flying upside down, and this maneuver is called a pull-down maneuver. So intuitively, you may expect a pull-down maneuver to look like this one here. You know, an aircraft performs a maneuver, a turning in this direction, so it goes down. But aircraft really don't perform such maneuvers because the reason for that is if an aircraft wants to follow a circular path like this, the g-force the pilot will experience will be in the up direction, right? So in this case, in the pull-up maneuver, the g-force is in this direction. So I'm sorry, it's going to be in this direction. So it will be increasing the gravitational acceleration, right? So the pilot will be experiencing an increased weight, in other words. But if you perform a maneuver in this direction, then the pilot will experience a reduced weight. And if you want to perform a very fast maneuver like that with a small radius, then there will be a negative g-force on the pilot. And the negative g, the human pilot cannot really endure large negative g loads. For example, a well-trained pilot can withstand up to 9G maneuvers, sustained 9G maneuvers. But for the negative case, as far as I know, the highest negative G-force anybody can withstand is 2 something. It's not even 3. And that's because of our body, right? In the positive G case, the blood goes towards our feet. But in negative G load case, all the blood will be flowing up to our heads. And in a human's head can literally explode if you want to perform a negative 6G maneuver, for example. It will be disastrous. So because of that, an aircraft don't perform these maneuvers, and a pull-down maneuver is the one defined like this. So you so anyway, the pull-down maneuver is very similar to the pull-up maneuver. If you write the forces, then just like this one, they will depend on the theta angle. If you can write them for this instance where theta is equal to 0, and for that case you have this equation, and then from there you can get an expression for the radius of turn and E omega. So here on this table you see the collection of the equations for all 3 turning maneuvers. For level turn, these are the expressions for radius and rate of turn. For pull-up maneuver, we have these 2 equations, and for pull-down, the equations are these. They are similar, but there are differences between them. So for the level turn case, we have this L square minus 1 within square root. But for the pull-up and pull-down, there is no square root term. But they all say the same thing. Whether it's a level turn maneuver or a pull-up maneuver or a pull-down maneuver, if you want a highly maneuverable aircraft, in all these cases you want a high load factor. Okay, so the high load factor is the key for all types of turning maneuvers, whether it's a pull-up or a level turn. Yani işte ancak bu şekilde olabilir negative G olması için. So for a negative G force to appear, you need to follow a path. You need to do a maneuver like this, right? I can't imagine any other way of getting a negative G force. So if you are turning so maybe you can get a negative G force in a turning maneuver like this. I'm not sure. Yeah, I think you can get a negative G force if you bank your aircraft in the other direction, right? So I guess if you just tilt the aircraft upside down, then the pilot will be sitting here, and he will be getting a negative G force. I'm not sure if you can make a turn like that. Okay, so as I said, pull-up and pull-down maneuvers are similar to level turn, with one very important difference that you don't really talk about sustained pull-up and pull-down maneuvers, because that will require the pilot to change the elevator and the throttle continuously throughout the maneuver. Rather than doing that, we just look at the instantaneous values. For example, we only consider the beginning of the maneuver where theta is 0, and at this instance, for the radius of turn and for the angular rate, we have these 2 equations. But when you come to the middle of the maneuver, when you are at theta is equal to 45 degrees, for example, then those equations are not valid anymore. But in this course, we don't really care about that. Well, it depends. If the aircraft is designed to perform such a flight, you can do that, right? I mean, let me show you. Let's take a look at this. Normally, let's forget about the pull-down maneuvers, and the aircraft can steadily fly like that upside down if it is designed to do so. So obviously, the lift force should be in this direction, right? For it to be able to fly like that, so you should have a lift force like this, and that will require, you have an airfoil here, right? Normally the airfoil will look something like this if you have a cambered airfoil. So the airfoil should be able to create a force in the opposite direction, and you can do that if you fly at the negative angle of attack, right? So let me show you so this is this is your airfoil. Normally this is what you have for lift force, but if you fly it at the negative angle of attack, then you can get a force like this. So that's what you need to have if you want to fly upside down. But if you fly it at a negative angle, so this is how you fly, for example, then in this case you will have a force in this direction, right? So that will give you, so this force you need. You can get such a force by flying at a negative angle of attack. So obviously the aircraft has to be designed to be able to fly like that. For example, the fuel system has to be designed accordingly. So I don't think a big cargo airplane, for example, can fly upside down like that, because the fuel, you have to have pumps to send the fuel from the tanks to the engine. Normally, you expect the gravitational force to be to help with the fuel flow, for example, but to be able to fly like that, you have to take that into account. So I already posted the sample final exams from previous years, so you should definitely look at those exams. Unfortunately, not all of those exams have solutions, but you should be able to solve the equations anyway. And those are the questions that were asked in the previous years, so those are at the level you should be able to answer. So please study the lecture notes and then try to solve the questions, and normally you should be able to solve them. If you can't, then I will be here on Friday. We can talk about that, or you can, if you can find me in my office, you can come and we can discuss those questions before the exam. So this is a final question from 2 years ago, I think. So this was, I asked this in the final, and for this case it's going down, straight down, and then the aircraft is going to perform this turning maneuver. And at this point you only need to consider the very beginning of the maneuver, where you have this force diagram. So in the vertical direction you have these forces. Thrust plus weight is equal to the drag. So this is one equation. And the second equation is this one. Lift force should be creating this turning acceleration. And to solve this question, this is the equation you use. Okay. Well, this really completes the course. So this was the last thing, last topic. Well, I didn't solve any sample problems in class, but again, as I said, you have very good questions from some previous year's exams, and I think if you study the lecture notes and solve those problems, then you'll be in a very good shape for this final. Then you should have no problems in solving the final exam. Okay, so as the last thing, I would like to show you this case. So this is a case where you have a negative g-force, right? So an aircraft flying through a path like this will experience a negative g-force, right? The pilot in there. While making this turn, the centrifugal force will be in the direction opposite to so it will be in the negative g direction, and if you can adjust everything properly, then you can make the acceleration people feeling inside equal to 0. And that is what they do to experience weightlessness within the atmosphere, right? And this is what they do to train the astronauts, for example, and people do that for fun. So basically what they do is aircraft fly through a circular pattern like that, and during that this portion of the flight, the net acceleration people in the aircraft feel can be set to be exactly equal to 0. So let me show you a video. So this is a commercial for a company who makes these flights. So it has audio. I'm not sure if you will be able to hear that or not.
Zero G is the most amazing thing you'll ever experience. Experience weightlessness without going to space, and that's aboard Zero G. We're the only company in the United States to be able to offer weightless flights, and we're very proud to do it.
It is real weightlessness. I mean, it is the exact same sensation I had for 949 hours in space, and it is such a feeling of freedom. You're flying by yourself.
Being able to fly weightless is like nothing on Earth. Some people have been scared, and I tell them this is the most zen-like, peaceful experience you're ever going to have. It's not a roller coaster. This is something where you're literally lying on the ground, and all of a sudden you start getting lighter and lighter and lighter, and you're floating, and it's an incredible experience. How do you describe eating chocolate for the first time? That's what it's like.
We start with the Martian gravity, 1/3 G, then lunar gravity, then to Zero G. Some people build up into that. The Zero G experience is just a phenomenal opportunity. Once you cross that threshold and experience it firsthand, it's something that sticks with you forever.
Everyone who flies on Zero G, no matter how old they are, whether they're 12 years old or 85, they're kids. They're having an incredible time. They're giggling, they're smiling, they're laughing. It's just something that you have to do in your lifetime. Every single person who's flown with us has been not only happy they did it, but they've wanted to do it again.
David was suggesting you have your Christmas party with us. I think that's clearly what we need to do.
Everybody who goes on Zero G is going to walk away with a flight suit. They're going to have a video reel of them flying through the air.
So I checked their website 2 years ago, and at the time they were asking for $5,000 for one flight. So that's a lot of money. But it looks like real fun. But the bad thing is, you can't really feel that for long. You can have a maximum of 30 seconds, because this is how you fly, right? Only during this part you feel weightless, and then you have to go through this one where you have an increased weight, and then you'll have another cycle. So you go through these cycles, like 30-second cycles, and so that's the best you can have. And there's this other video which shows this parabolic flight path. So this is a video of such a flight. So you clearly see that it's going up and then it starts going down. So right now people inside feel weightless. And according to this video, it doesn't even last 30 seconds. It's even shorter than that.
A vast virus database has been updated.
Yani işte o şey, they set the flight path so that the net acceleration becomes exactly zero, and that's not easy. So that's in fact I tried to make a problem for a final exam out of this, but it was too complicated and I didn't do that. If you look at the forces, it's not really that easy to set the entire everything equal to zero, because at the beginning you have the weight here, right? So this is the weight, and then there's thrust force, and then there's drag force, and then there's this lift force. So you have to set everything such that the net acceleration becomes zero. And just like the pull-up maneuver, you have to constantly adjust it at every point. So if you want, for example, theta is equal to, so I don't know, 40 degrees, you have a certain equality, but when you come here, it changes, right? So throughout the entire flight path, everything changes. And as I said, I couldn't really come up with an easy problem for this flight. Maybe I can do something for this point only. When it comes to this peak point, where the theta is equal to 90 degrees, for that point you can make certain calculations. So anyway, this is not really a part of the course. I just wanted to show you, since it is related to pull-up and pull-down maneuvers, and it's something fun. So by the way, if you go to YouTube, you'll find lots of videos for that. Obviously, you don't have to pay money to these people to experience that. You can do that in a small airplane. So if you know somebody who has a private pilot's license, you can just rent an aircraft and try that yourself. And there are lots of videos on YouTube. And I remember in one of those videos there was a dog in the airplane, and the dog starts floating and he freaks out. So anyway, this really completes the course. I hope you enjoyed it. And we covered lots of things in the last 4 or 5 weeks. But I tried to keep everything as simple as possible. I just want you to feel the basics, the basic physics involved in all these problems, rather than dealing with the details. So the equations we are using are as simple as possible. So please study the lecture notes. Take a look at past exam questions. Those questions are a very good indication of what you will be asked this year. So if you understand those problems fully, then if you can say that I can solve all those problems without any difficulties, then I can tell you that you should get a very good grade this year. So I will be here on Friday. I will not have anything new to say, but if you have any questions, we can discuss them on Friday. Or as I said, you can try to find me. It's hard to find me in my office nowadays, but if you can catch me in the office, we can go through your problems if you have any. So that's really all for me to say. Any questions from you? Okay, then I'm going to stop here. Do you have any questions, or is there anything you want to discuss regarding anything? It doesn't have to be just this last topic, but if you want to discuss anything from the previous weeks.